Hello and welcome to JHEP's lesson on lattice enthalpy, suitable for OCR and AQA. Edexcel and WAJEC, this should be suitable for you too, but you never know, I might be wrong. So, we have lattices in chemistry where we have two ionic compounds joined together with ionic bonds. Well, in an ionic lattice, we've got lots and lots of these ionic compounds all stuck together to make one big lattice. So for example, we have sodium chloride of salt, and we got a lot of those, and the energy between those two compounds in that ionic lattice has somehow got to do with lattice enthalpy. Well, let's break down what lattice enthalpy is, because if you remember back in AS chemistry, you would remember that enthalpy means energy. So we are talking about the energy in the lattice, or in this case for lattice enthalpy, the energy given out when two gaseous elements join together to make the ionic compounds. So the official definition of it is lattice enthalpy is the enthalpy change that accompanies the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. So the bigger the lattice enthalpy, okay, remember the lattice enthalpy will always be negative because we are forming a compound, and when we're forming, bond forming is exothermic. So the bigger the lattice enthalpy, the stronger the ionic bonds. And we are going to investigate how and when this statement comes into effect. Also, as it says here, lattice enthalpy is an exothermic change. So let's say that the lattice enthalpy for sodium chloride, and the way we write lattice enthalpy, is delta, big delta, delta H, subscript Le, standard conditions. Okay, let's say for example that is 2,400, I don't know, kilojoules per mole. Okay, remember kilojoules per mole is important because we are dealing with 1 mole, if we want to put it like that. So what affects lattice enthalpy? Well, number one is how large the ions are. So what I've done right here, I've actually drawn a relative size for them. But if we look at ptable.com, we can see that sodium would be smaller than potassium because it's got less electron shells and therefore less electron shielding, and the atomic radii for it will be shorter. So if it were joined to chlorine, a chlorine ion, because remember we talk about ions, it would be, the lattice enthalpy would be much tighter. It will be much more, just mainly because if you think about it, if you've got two little people hugging, you are more likely to say "oh" than a fat person and a little person hugging. You'd be able to feel more of the love with two little people than a fat person and a small. I know that's not a very good analogy, but this lattice enthalpy will be larger than this one. Okay, so that's minus 710, that's minus 2,400. Remember, we're giving off more energy over here than we are over here. Let's say that the K doesn't want to give off all its hamburgers. So what else affects lattice enthalpy? Well, their ionic charge. That's mainly because when we're losing electrons, we've got more protons to electrons. The proton to electron ratio does change, and that means there will be more protons attracted to the electrons, and therefore the ionic radii would decrease. The more protons we've got and the more the ionic charge is, the ionic radius does decrease. Also, we over here we want more electrons, shall we say, and we can get the electrons from anything in group 7 or anything with a negative charge. So why can't we actually measure lattice enthalpy directly in the lab? Why can't I just go to Imperial and just say, can I just measure the lattice enthalpy? Well, the thing is, we can't form 1 mole of an ionic lattice from its gaseous ions. Have you tried to get 1 mole of chlorine ions and 1 mole? Well, actually, that we can actually do that. But have you actually ever got 1 mole of sodium chloride? It's pretty hard, and also to get the energy to make that will be impractical. But there is hope. We can actually, due to this young dashing lad over here, we can actually find a different way to measure the lattice enthalpy. So this man, Hess's law, when you remember from AS chemistry, and this is very important for A2 chemistry as well, Hess's law states that if a reaction can take place by more than 1 route, and the initial and final conditions are the same, the total enthalpy change is the same for each route. So say for example, if we can't go like, that is a rubbish arrow, but if we can't go like that, then by all means we are going to go all the way around. So let's see the different way we can actually calculate lattice enthalpy. Even though, yeah, I was slightly a bit wrong when I was talking about that, but I'll come to that later. So, as you may know, when people fall in love, on the outside it may seem like that, like how did they fall in love? But there is a lot behind the scenes, and that is exactly the same for when 2 atoms fall in love. So, behind the scenes, not in front of the scenes, when it looks to everyone, it looks like we've just formed MgCl2 with magnesium and chlorine. But, and that's called enthalpy change of formation. That also is an AS chemistry thing, and we write the symbol like that, like this. So, behind the scenes, what happens behind the scenes? We have got MgS plus Cl2. We need this to be in a homogeneous, actually wrong word, but it needs to be in the same state. So we need them all to be in a gaseous state. Chlorine is already in a gaseous state, but we still need to do something to it. But let's look at magnesium. It's a solid now, and we need to make it a gas. So what we do, we atomize it. We atomize it so it becomes a gas. And that atomization process has an enthalpy, has an energy. When that actually happens, right, we gain energy, and that would be it would be, I don't know, plus 89. I'm looking at the book here, but plus 89 kilojoules per mole. And this process of changing magnesium from a solid to a gas is called enthalpy change of atomization. The definition for that is the enthalpy change of atomization is the enthalpy change that takes place when 1 mole of gaseous atom forms from the element in its standard state. So we have formed 1 mole of the gas from the element in its standard state, which was solid. So let's say that was 89 kilojoules per mole. And the shorthand for that would be delta H, yes, you guessed it right, AT, and then standard sign. AT obviously stands for atomization. Then the next bit that happens is that we need to atomize Cl2. It needs to actually separate. We can't have it, sorry, wrong, that's not supposed to be there. That we're supposed, it needs to split up into 2 chlorine atoms, okay, because we're changing them into atoms. Again, enthalpy change of atomization, we're not going to go over that again. The next thing that happens is that we ionize, okay. I will have to put a little disclaimer at the end, because atomization and ionization, especially when it comes to Cl2, can be swapped around. These orders can be swapped around, but let's not go into that. Don't worry about that. So we have got the enthalpy change of ionization. If you remember in AS chemistry, I think this is F325, I think. But what happens is that we remove an electron. We remove an electron from the 1 mole of the atom to make 1 mole of the gaseous 1+ ions. So what we've done, we've lost an electron from this magnesium gas to make magnesium ion. And we've got the electron over here. Nothing else has changed. And that's technically the definition of the first enthalpy change of ionization. Now, the thing is, over here, we have got 2 chlorine atoms and 1 magnesium. So magnesium, when it separates, needs to make a 2+ ion. If we look at the table over here, it's in group 2, so it's going to form a 2+ ion. So that means we would need to have a second enthalpy change of ionization. So we take another electron from the 1 mole of gaseous 1+ ions to make 1 mole of gaseous 2+ ions with the 2 electrons over there. Then, again, sorry, that's not supposed to be there. Yep. And then what happens is that we have an electron affinity where the electrons go to the chlorine atoms. Okay, when we gain electrons, that is called electron affinity. And the official definition for that, and I've got that on my wall, because you should put the definitions on your wall, that might help. But the electron affinity is the enthalpy change that accompanies the addition of 1 electron to each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1- ions. So in the next video, when we'll talk about the Born-Haber cycle, you would find out in experimental data that you will need to multiply it by 2, because we've got 2 chlorine atoms there. So we end up with this Mg2 plus 2 Cl minuses. Now we have got the ingredients we need for them to join together, for them to form, to make MgCl2, and this process over here is called lattice enthalpy. This lattice enthalpy will be negative, as I've said. This over here will be it will depend, but the first electron affinity would be negative as well. This over here will be positive, and this over here will be positive, and that over there will be positive. In the Born-Haber cycle, I'm just gonna sketch it out very quickly. It would look something like this, where we've got the formation over here. We've got the formation over here, then we've got the atomization here, then we've got the atomization here again. Then we've got the first electron, we've got the first ionization energy here, and then we've got the electron affinity here. Then we've got lattice enthalpy, and obviously, as we can see, we will end up back to where we have started. I know this is just a sketch. There will be a separate video on the Born-Haber cycle. So that is it for lattice enthalpy.